Good afternoon, everyone. This is Henry from A7 Tutoring once again with another math lesson today. We'll be building on what I taught yesterday about how to factor a trinomial and use that knowledge to graph a rational function or a rational equation. So let's take a look at our handy dandy decimals graphing calculator here. So we have the function y equals 2x squared plus x minus 15 all divided by x minus 1. But if you remember from yesterday's lesson, this numerator can factor out to be 2x minus 5. Whoops. 2x minus 5 times the quantity x plus 3. So you see it's the same graph. I've just factored because this is useful for if we have to graph this if we didn't have decimals. So first of all, we can start by asking where are the zeros of this function? Where does it cross the x-axis? Where does y equal 0? Well, if we want the function to equal 0, that means the numerator must equal 0, which means either the factor 2x minus 5 must equal 0, or the factor x plus 3 must equal 0. So let's go to our whiteboard over here. If 2x minus 5 equals 0, we can solve for the value of x. Add 5 to both sides. These knock out. We have 2x equals 5. Divide both sides by 2. This knocks out. And we have x equals 5 halves, which also equals 2.5. If x plus 3 equals 0, we can solve by subtracting 3 from both sides. And x equals negative 3. This algebra tells us that when it's crossing the x-axis, when y equals 0, either x equals negative 3 or x equals 2.5. So let's look at the graph and verify that. At this point where it's crossing the x-axis, x does in fact equal 2.5. The other point where it crosses the x-axis is negative 3, as we predicted by algebra. Now, you notice this blank space here, suggesting a vertical asymptote, a vertical line that the graph, the red curve, will approach but will never touch or cross. Where does the vertical asymptote occur? It occurs when you have a denominator equal to 0, which means the quantity x minus 1 would equal 0. So if we solve that, if x minus 1 equals 0, we can add 1 to both sides, and we get x equal 1. We should have a vertical asymptote at x equal to 1. So let's graph that line in decimals and see if that does in fact line up with being a vertical asymptote. So look at the blue line, the vertical asymptote. These red curves approach the blue line, but do not touch or cross the blue line. So if I zoom in, we can scroll down a little bit. We can see the red curve getting closer and closer to the blue line, the vertical asymptote, but it will not touch or cross the blue line. Similarly, if we go up, the red curve, the original function, will approach the blue line, the vertical asymptote, but it will not touch or cross that blue line. So we have verified that x equal 1 is in fact a vertical asymptote. But that doesn't tell the full story. There is also a slant asymptote. How can we solve for the slant asymptote? So let's see here. So let's erase some of this, so we have room to work. And how would we solve for the slant asymptote? So we can use polynomial division to evaluate the original function and take the limit as x approaches infinity. So the original function was 2x squared. Oops. 2x squared plus x minus 15. All right? Yeah, that's fine. Yeah, that's right. Okay. All right. Yeah, okay. 2x squared plus x minus 15. Right, that was the original function. And we're going to divide that by the denominator. Remember, denominator, divide. We'll use polynomial division. You could also use synthetic division, but to keep things simple, I will use straight polynomial division. What factor times x would give us 2x squared? Well, that's just 2x. Multiply it out, we have 2x squared minus 2x. We can subtract this entire quantity. Minus a negative 2x is the same as plus 2x. So we get 3x minus 15. So we add a plus 3 up here because 3 times x would give us 3x. This gives us 3x minus 3. Subtract this entire quantity, and minus a negative 3 is a plus 3, and we have a final answer of final remainder of minus 12. Oops. Minus 12. So we'd have the remainder, negative 12, over x minus 1. If we take the limit as x approaches infinity, this denominator down here gets larger and larger, which means the fraction gets smaller and smaller. So in the limit as x approaches infinity, this tail end drops out. We can approximate it as 0. And we have a slant asymptote of y equals 2x plus 3. This should be our slant asymptote. Let's verify that by graphing it on Desmos. Y equals 2x plus 3. So the green line is our slant asymptote. We can see that the red curve will approach, but it will not touch or cross the green line, the slant asymptote. Now, our work is not entirely finished because we have to consider where would the graph be above the x-axis, where would it be positive, and where would it be below, where would it be negative. So let's check that out. Once again, I'll clear the board so we have room to work. So remember that the factored form of this function again was 2x minus 5 times x plus 3 over x minus 1. The critical points that we have to look at are the zeros. So we draw a number line. We have 0 at 2.5. And we have 0 at negative 3. To the left of negative 3, when x is less than negative 3, 2x minus 5 is negative, x plus 3 is negative, and x minus 1 is negative. A negative times a negative is a positive. Divide by the negative is a negative. So we know in the region to the left of negative 3, the graph should be negative. Between negative 3 and 2.5, for example, let's consider 0. Let's consider x equals 0. In that region, 2x minus 5 is negative. X plus 3 is positive. X minus 1 is negative. A negative times a positive is a negative. Divided by the negative is a positive. So in the region between negative 3 and 2.5, the graph should be positive. Over here, when x is greater than 2.5, well, if x is greater than 2.5, then 2x minus 5 is positive. X plus 3 is positive. And x minus 1 is positive. Positive times a positive divided by positive will still be positive. So we should get this. Did I cover everything? No, I didn't cover everything. We have to consider the point x equals 1 also. Sorry, I forgot about that. We have to consider the point x equals 1. Between 1 and 2.5. When x is between 1 and 2.5, say it's 2. 2x minus 5 is negative. X plus 3 is positive. And x minus 1 is also positive. So a negative times a positive is a negative. Divided by a positive is still negative. So in the region between 1 and 2.5, the curve should be negative. So to the left of negative 3, the curve should be negative, below the x-axis. Between negative 3 and positive 1, the curve should be positive. Between 1 and 2.5, the curve should be negative. And to the right of 2.5, it should be positive. Let's look at the graph and see if this algebraic prediction fits the graph. So to the left of negative 3, you can see that the curve is negative. Between negative 3 and positive 1, the red curve goes positive. That agrees. Between 1 and 2.5, the curve should be negative, which it is. You can see in this region here, between 1 and 2.5, the curve is negative. Then as you go further out to the right of 2.5, when x is greater than 2.5, the curve becomes positive again, which again agrees with our algebraic prediction. So we must consider the key critical points determined by the individual factors that would give a 0 either in the numerator or the denominator, and check the regions in between those critical points to determine in those regions if the graph is positive or negative. Armed with this information, knowing whether the curve is positive or negative, and the vertical asymptote and the slant asymptote, you could draw this red graph, the red curve, by hand if you did not have a graphing calculator available. I graphed it on Desmos to show you that yes, this all works, and yes, an actual graph provided by the computer does agree with the algebraic predictions based on the analysis we did of the original function. This has been a simple lesson with an example of how to graph a rational function, building off yesterday's lesson of how to factor a trinomial. If you'd like to learn more, I'm available for hire as a private tutor. Here's my website. Here's my email address at the top. Let me erase some of this so you can see clearly. So again, my contact information up here. The first 1-hour lesson is free for all new students. Try before you buy. You take no financial risk. The burden of proof is entirely on me to demonstrate outstanding value in helping you succeed in math. Also, as a thank you for watching all the way to the end of today's lesson, if you mention the code FREEBOOK when you contact me at our first lesson, the free trial lesson, I will give you a free copy of my book, Smart Suggestions for Student Success, which is intended to provide advice that will help students, especially high school students and college students, succeed in school, in work, and in life. Thanks for watching. Bye-bye.